Okay, so here's where we were last time. I hope everybody had a good 4th. Nice day off. After a full 2 days of multivariable calculus, you get a holiday. Nice way to start the term. So here's what we were talking about last time. We were talking about this idea of orderings and natural ways to describe a given choice of ordering. I mean, you can talk about a pair of vectors v and w just as here they are. It's 2 vectors, no particular order. But once you put them in an order, once you say, look, I want to talk about v comma w, where very specifically v is to be thought of as being the first one, and again with the that's so weird. Okay, well, I don't know why this little. I'll have to call somebody about that. Okay. And then W is to be thought of as being second, right? So how can we describe the ordering, right? Not the pair of vectors. The pair of vectors, just there's nothing intrinsically ordered about the pair. But once we order it, how do we describe the ordering? I think a reasonable choice here. Let me look at how I've got this order. I've got V first and W second. You look at the geometry of these 2 vectors, and with this being first and that being second, in other words, with the ordering going that way, right, first to second, and counterclockwise is hard to argue with as a good choice for how to describe that. Right? So what we ended on last time, after making this observation, and of course if you do it the other way, W comma V, then it's clockwise, right? Was the question of, is there a sort of a 3-dimensional version of this? So in other words, instead of 2 vectors in a 2-dimensional plane, for which we have now a notion of order, what if we have 3 vectors in a 3-dimensional space? And is there some sort of analogous, notion of order? So it turns out that there is. Now, before I write that down, I want to talk about some features that this choice has, because clockwise versus counterclockwise. And that is, if you, let me erase this. If you switch the 2 vectors, right? So notice we did a little switcheroo there. Having switched the 2 vectors, that changes the order. Clockwise becomes counterclockwise. Counterclockwise becomes clockwise, right? It doesn't really matter what the ordering of the one is. If you switch, it becomes the other. Okay. Here's another feature that this has. If you were to take a pair of vectors, let's say here's a couple of vectors, right? If you were to look at their mirror images, right? If this, first, second, I'm going to do this from y'all's point of view because it's opposite, from my point of view, right? But if this is first and that's second, then you'd call this a clockwise ordering. The mirror images in the same order, these being first, those being second, in the same way that this, first, second, is a clockwise ordering, this is a counterclockwise ordering. So mirror images are opposite orders. And switches become opposite orders. So we have a couple of symmetries, I'm going to call symmetries of this choice. All right, so when I say, is there a 3-dimensional version of this, I'd really like to find a 3-dimensional version of this that kind of has these same sort of symmetries. All right, so the way we do it is with the right hand, the human right hand. By the way, this was the hardest figure in the book to draw. It took me quite a while. I think it was a couple of hours of crumpled heaps of paper on the floor after failures. So here's the idea. Suppose I have an ordering, suppose I have a trio of vectors. Let's see, where do I have that? Okay, this is where we start. Suppose I have a trio of vectors, A, B, C, and I'm going to put them specifically in this order, A, B, C. And I want to talk about, what can I say about this ordering? Whoops, I wanted that in the highlighter. This ordering here, where the A vector is first, the B vector is second, and the C vector is third. And I haven't put the C vector on the page yet. We'll get to that in a minute. Okay. So here's the idea. Use your right hand Has to be your right hand. You can't alternatively say, I'm left-handed, I'm going to use my left hand. Sorry, it's got to be your right hand for reasons that we'll talk about in a moment. But there's a certain hand gesture that you make. It has to be this specific hand gesture. You're not free to do any sort of, alternative hand gestures. The gesture is as follows. You have to point your index finger in the way that your index finger wants to point, parallel to your palm. That's critical. Index finger parallel to your palm. Your middle finger, bend it the way that your middle finger wants to bend. Don't do any hand yoga. That's not okay. Right? You got to bend the middle finger in the way it wants to bend. And with those rules in place, so index finger like that, middle finger bending the way it wants to, do what you have to do to get your right hand such that your index finger points in the direction of the first vector, your middle finger in the direction of the second vector, right? So how much you bend that middle finger, it depends on what kind of vectors are we talking about here. You might have to do your hand like this or like that, or try not to make a rude gesture. And the point is, get your hand arranged to where index finger in the direction of the first vector, middle finger, second vector. Now, notice these two vectors, the first two vectors, A and B, they define a plane. Right, here's a plane defined by A and B. And this kind of cuts the three-dimensional space in half, as it were. There's an upper half in this case, as it turns out, and there's a sort of a lower half. But more specifically, there's the one side and then there's the other side of the plane. Well, having noticed that A and B define this plane and having arranged your fingers like so, notice that your thumb points in a very clearly, conspicuously chosen side of the plane. In this case, these two vectors A and B, the thumb is pointing to the what you're going to want to call the upper side of the plane. Yeah? All right. So if the third vector, give me 2 seconds. If the third vector points to the same side, the third vector points to the same side that your thumb does, then we say that list, A, B, C, is in right-hand order. Right? On the other hand, no pun intended, if the third vector had pointed that way, right? I mean, just a trio of vectors. I mean, maybe the first vector like that, second vector like that. If the third vector was down, that way, well, notice that your thumb is pointing on the opposite side, right? Your thumb's pointing on one side of the plane. The third vector is pointing on the other side of the plane. That is not right-hand order. In fact, if you think about it, you might want to call this left-hand order. Because, now let's do the same thing with our left hand. One, right, index finger, doing what index fingers want to do, pointing. Let's see, how can I bend my middle finger? Now, I'm not allowed to do the hand yoga, right? I can't just do so I have to bend my middle finger that way, which in order to get it to do what that vector is doing, I'm going to have to do this. And then notice that my thumb now does point on the lower side of the plane. The third vector points on the lower side of the plane. As I have that purple vector drawn there, you might want to call that a left-hand order. You had a question.
Can you just explain the purpose of the plane again?
Yeah, that's right. So the point is, you might not necessarily have vectors that are all perpendicular to each other exactly, right? In other words, that third vector, it might be like this, it might be over there. I mean, there's lots of different kind of ways it might point, all of which are on the same side of the plane, right? So there's a huge number of possibilities of how these three-dimensional vectors might point. And I don't want to say that they have to be exactly, right angles, exactly perpendicular. Not at all, right? Just I want to distinguish, kind of roughly speaking, two different possibilities from each other. And being the first two vectors defining a plane, that says the third vector, look, it's either on the one side or it's on the other side. It's a very sort of flexible distinction. Yeah, is that cool?
Well, I was thinking what was the motivation for the particular location and angle of the plane? Why?
This is an arbitrary choice. Yeah, this is an arbitrary choice. No, yeah, we're kind of making this up. Now, it turns out that this arbitrary choice that we're making is going to have some remarkable mathematical properties. Yeah, it's so my motivation is stuff I haven't told you yet. Yeah, right. Yeah, exactly. Okay. All right, so we have this idea of right-hand order. This trio of vectors, as I've got them drawn here and listed as, A first, B second, C third. This is a right-hand order. Okay, now I claim that this choice that we've made, this designation of right-hand order, I claim this is kind of analogous to clockwise, counterclockwise in the following two senses. This is got both of those symmetries. So if you take two of the vectors on this list and switch them. Let's take the A and the B, for example, and switch them. If you do a switcheroo, right, if we make B first, A second, and C third, this is now not a right-hand order. ABC was right-hand order in this, case. Now, B being first, A being second. Okay, well, again, right hand. If B is first, right, A is second. Well, I'm going to have to do like that to get my middle finger. I mean, I can't do like this. I mean, I have to, but one way or the other, I have to orient my hand. I guess I could go. I'm not quite flexible enough for that, but one way or another, you got to orient your hand in such a way that with your index finger still pointing in the B direction, the first vector direction, your middle finger is pointing in the second vector direction. And notice that now my thumb is pointing down, not up. Right? So BAC, not in right-hand order. Or said differently, BAC, left-hand order. So doing a switcheroo with two of the vectors, you change the A and the B to the B and the A, switch two vectors, what was right hand becomes left hand. And by the way, this is a fairly reasonable sort of hand-waving description of why that is, right? In other words, index fingers, middle fingers pointing in the same directions of the right and left hands. Notice the thumbs point in the opposite directions, thus indicating that they're opposites in terms of the direction that third vector can point. Okay. All right. Secondly, mirror images. This one's actually pretty easy to argue. A trio of vectors that's in a right-hand order. If you look at their mirror images, left-hand order. Right? Arguably even easier to see than the whole clockwise, counterclockwise thing. Okay. All right. So the same kinds of symmetries. Okay. All right. So this is this is a notion that we need to have down before we can give a full discussion of determinants and cross products. Remember, cross product is really our primary interest in this section, but I think right-hand order is a very useful idea to have in mind as we go along. Okay. So let's set that aside and move along to determinants. Like I say, I'm not going to be able to give a full discussion of determinants in Math 212. I'm going to give you just a sliver thin discussion of determinants because it's a very deep subject, in fact. Right? So anyway, here it is. There's the formula for the determinant of a 2x2 matrix. It turns out that this deceptively simple little formula is surprisingly interesting. Surprisingly cool things are going to happen. Okay. Here's the formula for the determinant of a 3x3 matrix. Now you notice we're using this notation here, this alternative notation. It looks like absolute value. That's unfortunate. It's not intended to be absolute value, and it's not intended to suggest that determinants are positive either. They are perfectly able to be negative, right? So that expression has no relation to absolute values. Nevertheless, gets used sometimes. So I'm using that notation here to tell you the determinant of a 3x3 matrix. Now you might wonder what is going on with this minus sign right here. Is that a typo? It's the only minus sign in the formula, right? There was a plus here and there's a plus here. So what's with the minus there? It has to be there for this to be a surprisingly interesting formula. If you put a plus in that place, you get useless, irrelevant expression. It doesn't do anything interesting at all. Ditto this minus sign here. Very important. It's got to be minus. Okay, so for the moment, think of these as, arbitrary, handed down stone tablet formulas, and we'll see momentarily why they're interesting. Yeah.
Okay, I was going to ask if there's any way to intuit that.
No, it's really hard. I mean, yes, there is, but we're not going to be able to get there in this course. All I'm going to be able to tell you is that if we do these formulas as written here, arbitrary and weird though it seems, great stuff happens. Yeah. Right. Okay, so here's some cool facts. Suppose you have a couple of vectors. A vector A and a vector B. These are vectors in R2. Now I'm going to do two things with these vectors. The first thing I'm going to do is I'm going to take this pair of vectors, I'm going to use the coordinates of the first one to make the first row and the coordinates of the second one to make the second row, thus defining a matrix. Now, if you give me a couple of two-dimensional vectors, I can put them together in this way. Why I would want to, we'll see momentarily. Okay, now here's another thing I could do with these vectors. I could take those two vectors, let's draw them. So first vector, let's say like that. Second vector, let's say like that. And I could make the parallelogram that these define, if you will. Right. So I've taken these two vectors, I've created an algebraic object, namely a matrix. I've created a geometric object, namely a parallelogram. And here's why determinant is interesting. It turns out that the determinant of this matrix is very closely connected to the geometry of that parallelogram. And in a way that's really hard to see coming, but here it is. These vectors, note that as I've drawn them here, this is a counterclockwise ordering. A counterclockwise order means that determinant will be positive, and vice versa. If the determinant is positive, it means you have a counterclockwise order. That is a shocking result. That seems way too simple. I mean, at a glance, correct me if I'm wrong, if I were to give you a pair of vectors and maybe, in such a way that you can't just kind of draw the plot. I mean, what you'd be inclined to do is to take the two vectors and use some arctangent formulas to figure out what certain angles are and see which one's got the bigger angle, which one's got the smaller angle. And then you determine from that if it's clockwise or counterclockwise. You don't have to use arctangent. This says we have this three-function arithmetic formula that will answer the question for you. That's shocking. Okay, so that's the start of it. The second thing is, let me go along in those same lines. If it's a clockwise order, the determinant will be negative. And finally, if it's neither clockwise nor counterclockwise, for example, they could be parallel, or one of the vectors could be 0, or one of these sort of anomalous, kind of weird kind of things, then the determinant will be 0. So the determinant, the very weird and arbitrary formula that we wrote down, seemingly meaningless algebra, but it's intimately connected to the ordering that we have of the vectors. And keep in mind, there's a well-defined order here. This one is first, as per the fact that it's the first row. This one is second, as per the fact that this is the second row. So determinant tells you order. Fascinating. Here's the other thing that I've been sort of sweeping under the rug here. The determinant tells you something else in the sense that the absolute value of the determinant tells you the area of this parallelogram. And that's another real shocker, right? I mean, if I were to ask you to compute the area of that parallelogram, you'd be thinking in terms of dropping a perpendicular and measuring the length of the side. And, well, the length is going to be a square root. And when you drop the perpendicular, you'd be like, wow, that's, how do I drop that perpendicular? Because it's not a straight up and down thing. And you've got a non-trivial geometry problem that you feel like is going to involve square roots for lengths. And doesn't sine theta come up in the formula that you all memorized in geometry class back in high school? Shouldn't this have trig and square roots in it? And answer, no. The formula for the area of a parallelogram, 3-function arithmetic. Shocking. Okay. All right. Let's go to the 3-dimensional version of this. The 3-dimensional version starts very similarly. Suppose we have, but now it's 3 vectors. First vector, second vector, third vector. 3 vectors in R3. And I'm going to say, roughly speaking, the same theorem is true. And what I mean by same is exactly what you would expect. Again, here we have these 3 vectors. We can make a parallelogram. Oh, excuse me, it's not a parallelogram. This is 3-dimensional. A parallelepiped, they call it. All right, you can look at this parallelepiped. Whoops, sorry. Yellow, here we go. All right, parallelepiped. And you can look at the way those 3 vectors are oriented in space, and you can talk about, on the one hand, the volume of the parallelepiped. You can talk about the handedness of the listing, with A first, B second, C third, right? And with those vectors in that order, A first, B second, C third, determinant does the analogous thing. So in the sense that the order is based on the sign of the determinant, right? Positive means right-hand order. Negative means left-hand order. 0 means neither right-hand nor left-hand order, which by the way would be, for example, a trio of vectors that are coplanar, right? Where that third vector, it's not on the one side of the plane, it's not on the other side of the plane, it's parallel, annoyingly, to the plane, right? Sort of in between. So determinant, by its sign, tells you which it is. And also, the magnitude, the absolute value of the determinant tells you the volume of the parallelepiped. And that's actually a really hard question if you think about it. I mean, think about high school geometry class, and if somebody gave you this wacky angled non-right parallelepiped and asked you to compute the volume of it, oh my gosh, really hard problem, right? Easy problem. Take the determinant, take the absolute value. Yep.
You can also arrange the vectors in columns rather than rows.
You can. That's true. We're not going to do much with that in Math 212. That's one of in this long list of other facts that are true about determinant. The many days of lectures that could be made about determinant. That's on the list. But yeah, true fact. But you don't need to worry about it at this stage. Yeah. Okay. All right, so really surprising facts. So determinant is a really interesting thing. So here's an example, by the way, and this is a very plug-and-chug example, so let me be quick about this. But here's a trio of vectors. What's the volume of the parallelepiped? Well, so as we just discussed, you take those 3 vectors, make a matrix, take the determinant, and that tells you everything you'd want to know about that parallelepiped. For the one thing, the minus sign here tells you that this listing is a left-hand order, right? And the 10 here tells you that the volume is 10. Everybody good? Okay. All right. Okay, so now, what does this have to do with cross product? So there's this second product. And we talked about dot product last time. And okay, cool, we have a way to multiply vectors in some sense, and it's geometrically natural in certain ways. This is the other one. The other way that I claim is both a product in the sense that it algebraically kind of behaves like a product, and also is geometrically natural, but in very different ways. I'm gonna do the same trick that I did with dot products, which is I'm just gonna write down a formula that seems very arbitrary and out of left field, and where did this come from? Did I just pull this out of thin air? And then I'm gonna, over the next several minutes, show you some amazing properties that it has that are very geometrically natural. So here's my arbitrary formula. No justification, no motivation given. Let me comment while I'm here. This has got to be an R3. The dot product applies to any pair of vectors in any... You could talk about dot products in R17. Totally cool. The cross product as an operation on two vectors only makes sense in R3. Not R2. There is no cross product in R2. There's no... what I'm going to call binary operation cross product in R4 or R5 or anything higher. Now, asterisk, there is an algebraic construction that kind of plays the role, but it's not a product in the sense of you give me two vectors and out comes another vector. So, as a binary product, only R3. Okay. All right, so we write down this formula. Now, just like with the dot product, I'm going to start by writing down some algebraic properties. You can check these algebraically, just plug and chug. There's nothing deep going on here. Let me rephrase that. You can prove these formulas without making any deep arguments. I'm going to make some deeper arguments momentarily. They'll kind of come back to put these in perspective. But these are all plug and chug. Like take this first one. You can just compute V cross W. You can compute W cross V and confirm that equation is true. And it's just make this plug and chug. Okay. So it's a little bit of a yawn because you look at these properties and it's like, okay, come on, I've seen algebraic properties before. I mean, this is, come on, man, they made me learn algebraic properties back in high school. And is there anything interesting going on here? If you take a closer look, you will notice that, there's some actually pretty weird things going on here. What's the deal with that minus sign? Right? So very importantly, the cross product is not commutative. But it's worse than that, arguably. It's the exact opposite of commutative. So it's not only unexpected, it's unexpectedly organized. It's not organized in the way that we would expect it to be, and it is unexpectedly organized in a way that we wouldn't have guessed. That is really surprising. So we're going to have to figure out what the deal is with that minus sign, and we'll talk about that over the next little while here. Okay. This next one, also pretty weird. If you take a closer look, notice that we have here, we're doing dot products and cross products, but the vectors, it's not like this is a distributive deal or anything like that. The vector that was inside of the cross product in the first one, that is not inside of the cross product in the expression that it's equal to. That's weird. Okay. Likewise with the others. I will draw your attention to one fact here, and that is all three of these expressions, this is just for symbolic purposes, but let me just write UVW. Notice that this one has the vectors in that order. This one, I need to change the color, sorry. This one, WUV, it's sort of a different order, but it's kind of going around this little loop the same way. It's still kind of clockwise around this loop, if you will, right? And then the last one, VWU, again, clockwise around the little loop in the same order. So, how about that? Yes?
So does it matter which order the cross product is?
Oh, yeah, it does. Absolutely. You get a minus sign if you switch the order inside the cross product. Absolutely. Yep. So notice there's 6 different ways to arrange 3 vectors. These 3, blue, green, and yellow, all give the same value. The other 3 are going to relate to these three by way of them being, as you know, the cross product being in the opposite orders, and therefore you will get a minus sign. Yeah. Yes. This is a numerical value. That's a great question. So that's another thing I wanted to talk about. So let me go to that. We made a big deal last time about how the dot product of two vectors is not a vector, and that was weird, right? So I should mention, and thank you for the reminder, the cross product of a vector and another vector is also a vector. So this is arguably more expected. The cross product of two vectors gives you a vector. So now you got to look at this expression here. Here we have, let's see, V and W are vectors. Therefore, V cross W is a vector. So this is a vector U dot another vector, and vector dot vector is scalar. Right, absolutely. Okay, and by the way, please do be careful when you're writing down algebra of vectors. Make sure that you don't ever put a square peg into a round hole. So, for example, you can talk about, hypothetically, if you wanted to say U cross V cross W, that is meaningful in the sense that, well, that's a vector, and that's a vector, and I can take the cross product of two vectors. But don't write down, under any circumstances, this, because that doesn't make any sense, right? And no matter how you do the parentheses, U dot V, sure, you can do U dot V. That gives you a scalar. And it doesn't make any sense to talk about a scalar dot a vector. It's not a thing. Right? Square peg, round hole. Okay. All right, so heads up. Okay. All right, so we have some kind of eyebrow-raising properties of the cross product. Here's another one. Now, this is the first one that's sort of geometrically... well, anyway, let me just say this is an interesting geometric property of the cross product, and that is that the cross product of two vectors is always orthogonal to both of the input vectors. So V cross W is orthogonal to V, and it's orthogonal to W. Okay, how about that? Now, why is that true? This is a plug and chug problem. I'm going to leave this as an exercise for you guys. Now, I hope y'all all had knee-jerk reactions per my suggestion last time. When you see that word orthogonal, the very first thing you should think is, oh, somebody said orthogonal. That means a dot product's equal to 0, right? That's how you test for orthogonality. That's the definition of orthogonality. Dot product is equal to 0. So if you want to check that the cross product is orthogonal to, for example, V, well, then you take the dot product of V and the cross product. Right? So plug and chug. Right? You can compute this out. You have a formula for the cross product. You have a formula for the dot product. Crank. There's only 6 terms. It's not that bad. Everyone should do this once in their lives. It turns out you get 0. So as it turns out, not hard to see, the fact that this dot product is equal to 0, that tells you that the vectors that you dotted are orthogonal. Everybody good? Okay, so everyone should crank that. And then likewise on this one, that shows that W is orthogonal to the cross product. Okay. Now there's a little bit of algebraic trickery that we need to pull so that we can get on with some cool geometric stuff. We just have to kind of stare at this and notice that, wow, sure enough, this works. So here's our formula for cross product. By the way, I hope you won't memorize this formula. There's a much better formula I'm going to show you in a few seconds. I guess you could memorize this if you want, but I think it's a bad idea. Anyway, there's that formula. Here's an alternative way to write that formula. Now let's take a peek. So what's going on here? Well, you'll notice that this formula is basically telling you what the coordinates are. The coordinates are, the coefficient of E1 is the first coordinate. coefficient of E2, don't forget that minus sign that I've stuck in there, seemingly weirdly. I'll explain why in a moment. That's the second coordinate. And the coefficient of E3 is the third coordinate. So this thing that I've written down, if you look at those coordinates, each of those coordinates is a 2 by 2 determinant. 2 by 2 determinants, you can, blah, blah, minus blah, blah. Don't forget that little minus sign in the green one. And it turns out you get exactly this. And I've already forgotten the colors. Let's see here. Blue, green, yellow. So you get exactly that, and that. It's just algebra. Again, everyone should, write it down and observe that, well, in fact, sure enough, that's true. Okay, having observed that, now let's look at this formula. And in fact, that looks, cosmetically anyway, just like the formula for a 3 by 3 determinant. Even down to the plus, minus, plus pattern on the signs. That's exactly the formula for a 3 by 3 determinant. So, that's weird. So we have now an alternative way to memorize the formula for the cross product. This is the only formula for a 3 by 3 this is the only formula for a cross product that I've ever memorized in my life. Right? Don't memorize this one. It's too easy to get it confused. Wait a minute, is it V2W3 minus V3W2, or wait a second, was it V3W2 minus V2W3? Oh, which way did it go? They look so similar to each other. It's real easy to get that messed up, right? This one, no such worries, because it's a real simple pattern. Put standard basis vectors in the top row. First vector goes in the next row. Second vector goes in the last row. Just write them down, and then just make sure you know how to compute a determinant, a 3 by 3 determinant. And the determinant will kind of do the bookkeeping for you. Where does the minuses go? Where do the pluses go? The determinant is set up perfectly to do that for you. So since you have to memorize the formula for determinant, you might as well let that do the work for you here in allowing you to compute cross products. Okay. All right. Now, analogous argument. This seems going to seem weird at the start, but let's look for, how would I write down? I've got V cross W, but now I want to dot it with another vector U. How would I do a dot product? Well, okay. Let's see. I'm going to have to zoom out. Fortunately, we have this gigantic screen that we can look at, and I hope that might still be. Is that still kind of visible? Hopefully. Some of y'all are sitting close enough. But anyway, recall these are the coordinates of the cross product. Here, let me circle those in a consistent color. Here's the formulas, the coefficients in the cross product. And when you do a dot product, what you do is you take those coordinates and you multiply them by the coordinates of the other vector and then add. Right? So just, straight up directly from the definition of a dot product, multiply and add coordinate-wise is how I'd compute the dot product of U with V cross W. And then you look at this expression and notice that is a 3 by 3 determinant. Right? So this is a extremely important formula, and it's again kind of algebraic sort of trickery that gets us to it. But notice that when you're doing this little weird construction for whatever reason, the first vector becomes the first row, the second vector becomes the second row, the third vector becomes the third row, and you just take a determinant. So, wow, isn't that weird? We already know that this is a natural thing. Determinant that's a natural thing. That means something. geometrically, it's natural, right? Therefore, since it's algebraically identical to this thing, that thing is geometrically natural. So we give it a name. We call this a triple product. And triple product, in fact, is just kind of synonymous with determinant when you're talking about 3x3s. Okay, so this ends up being a really important fact. I mean, roughly speaking, how we're going to take advantage of this in this course is we're going to capitalize on the fact that, well, we already know cool facts about the dot product. We already know how to think about dot products geometrically. We already know how to think about determinants geometrically, and we're going to use that to help us make good geometric sense out of the cross product. That's what we're sort of aiming for. So, standard trick in math is if you want to understand something, relate it to things that you already understand, and then work from there. Okay. All right. Okay. So triple product equals determinant. Very cool. All right, so here's a great way to think about this old fact. So we know that. Let's see. Where did I write this down? Yeah. Okay. So here we go. We've just got through stating a few minutes ago that the cross product is orthogonal to both of the input vectors, and I told you guys, all right, well, plug and chug. Algebraically, just write down the terms. Turns out they all cancel. You get 0. Dot product being 0 means orthogonal. It worked. There's something unsatisfying about how that argument works. I want y'all to do that, right? Plug and chug. It's very bulletproof, which is always good for a mathematical argument. But there's a better way to do it in the sense that there's a way that's more geometrically intuitive, and that goes as follows. So if I want to prove that the cross product is orthogonal, let's recall that we just needed to show that these dot products are 0. Right? That's what orthogonal means. Dot products are 0. So if I need to show that these dot products are 0, well, now here's where I can take advantage of the big formula on the previous page. Those dot products I can now recognize as triple products. Triple products are determinants. Determinants relate to volume. So I can relate the question, this is kind of weird, I can relate the question of orthogonality to dot products to triple products to determinants. There's a little train of connections here, but ultimately I've related the idea of orthogonality to the idea of volume. And that's pretty cool, right? I haven't done any cranking. I haven't, plug and chug and expand the whole thing out and write the whole thing down and, just algebraic, mysteries of, how does the cancellation work. We've just observed that the geometric question of orthogonality happens to be the same as the geometric question of volume in this case. And specifically, the vectors are V, and W. I just need to know what's the volume of the parallelepiped that's defined by these three vectors, V, and W. Is that a parallelepiped? I mean, this V and W? It seems like we're listing the same vector twice. Well, we are. V, and W. And how much volume is in that box, right? Now, just for geometric sort of effect, here's three vectors. You can imagine these three vectors defining a parallelepiped that makes a box, in other words, and how much volume is in that box. Well, if two of the vectors are the same vector, you can just imagine as you do this, as the two vectors become the same vector, the box becomes flat, right? It's recycle ready. How much volume is there inside of that box? 0. It's a flat box. No volume. Let's see here. The volume is 0. Therefore, the determinant is 0. Therefore, the triple product is 0. Therefore, that dot product is 0. Knee-jerk reaction, dot product was 0. orthogonal. Everybody good? I love this argument because it connects so many different ideas that are, again, at a glance, kind of seemingly unrelated. And it allows us to avoid a little bit of tedium in the, cranking it all out. Okay. All right. Here's another fact. This is another little mathematical bank shot. Remember I was talking about that last time, I guess it was. Very often in math, if you think about some object you don't actually care about, and if you compute it in two different ways, I don't care about this object, but having computed it two different ways, then you have a relationship between two other things that you might actually be interested in. Right? And that's what's going to happen here. So the theorem I want to address is this one. That is, if you take a couple of vectors, v and w, and if you make a parallelogram out of these two vectors. Didn't we do that already? Two vectors make a parallelogram. That was in R2. These are now vectors in R3. Two vectors in R3 make a parallelogram. We have not done this before. It turns out that the cross product of those two vectors, the magnitude of the cross product is equal to the area of that parallelogram. Turns out to be true. Okay. Again, I'm going to prove this. There's a couple different ways to prove this. One is you could just laboriously crank, right? Massive cranking terms, equations everywhere. It's a nightmare of inconvenience. Let's not do that one. All right. Let me show you the slick move. The slick move here is to, in trying to relate the length of the cross product to the area of the parallelogram, I'm going to consider instead a third thing that I don't care about. Right? Again, here's this mathematical bank shot. I don't actually care about this 3x3 determinant, this triple product. But by calculating this thing two different ways, the things that I am interested in are going to pop out, and sure enough, everything's going to work out great as it turns out. So this is a very tricky move. So here we go. I'm going to think about that thing that I don't care about. V cross W, V, and W as a matrix taking the determinant. All right. So calculation number one. A determinant is a triple product. Now, let's be careful with this. First vector, second vector, third vector. Determinant is a triple product. Yeah? And, well, wait a second. Now, having seen that determinant that I don't care about is a triple product, and noticing, well, the triple product ends up being a dot product of a vector with itself. Wait a second. I know what that is. That's magnitude squared. And I've gotten sort of an unexpected, interesting first half of the calculation. Now, what was my motivation, by the way? I'm going to pull back the curtain a little bit. The reason that I wrote down this particular thing is because, I was scheming to make this triple product be a dot product of a vector with itself. So it's an obvious scam, right? Hack, if you want to call it. I did it that way so it would work out nicely. Anyway, there it is. Okay. So that's the first half. Now, keep in mind, our goal is to compute this thing two different ways. That was the first one. I now want to look at this thing and argue, well, look, it's a triple product. It's a determinant. Therefore, it's a volume. Right? Determinants are volumes. Whoa, slow down. Absolute value. How do I know? What if this was negative? Any chance that determinant could be negative? I claim that determinant can't be negative, and the reason why is on the page as we speak. You want to observe why it is that can't be negative. It's a square of something. Right? This is the same as that. It's a square of a magnitude. Squares can't be negative. Yeah? Okay. All right. Okay, so that means that this determinant is a volume. I don't have to worry about absolute values. That determines a volume. It's a volume of what? Okay, well, I've got to play the game. It's the volume of the parallelepiped that's defined by, well, these three vectors. So let's write down these three vectors. Let's see, V, W, and the cross product. Here they are, V and W. And here's the cross product. Recall, we already know that cross product is perpendicular to the other two vectors. That means it's perpendicular to this entire base. And that means this is a kind of you might call this a right parallelepiped. I mean, it's partially right, at least. And now I'm going to remind you of an old formula from way back when, high school geometry. If you have any sort of a cylinder, by which I mean some shape, and then you drag it perpendicular by some distance, which is what we have here. We have this yellow parallelogram down there, and then it's been dragged perpendicular to itself per that purple vector. Right? Then the volume is just the area times the distance. Okay, so this volume here, let's see, I'll do this in orange. That volume is the distance that I've traveled, I have in purple, times the area. Area of that base. Okay. All right, so that's what I have here. Again, we started off by computing this thing. I've now computed it two different ways. On the one hand, by a triple product argument, we see that it's equal to the magnitude squared. By a volume argument, we see that it's area times distance. Therefore, these two things are equal to each other. Cancel one factor of magnitude with that factor of magnitude, and you have magnitude of the cross product is equal to the area as desired. So the total mathematical bank shot, again, we started off with this green determinant for no apparent reason. It does not seem to directly relate to what I'm interested in, but it worked out. So again, this is another one of my favorite arguments it's really one of my favorite arguments in the course because it's so sort of like unexpectedly connecting all these different ideas and allowing us to draw a powerful conclusion and avoid massive messiness of tedium by just being clever and using what we know about the connections between these ideas. Okay. All right. This is the same theorem, just kind of said a different way, just observing that the area of that parallelogram could be computed like so. So it gives you an alternative formula for the length of the cross product. Yeah, whatever. Okay, last question that I want to address, and we got to move on. I'm behind schedule, as always. So here's what we know about the cross product so far. If you give me two vectors, V and W, we already know that the cross product is going to be perpendicular to both of them. So it's going to be parallel to this line that's perpendicular to V and W. So between V and W, they define this line of perpendicularity. We know the cross product is parallel to that line, and we know that the area of that parallelogram tells us how long the cross product is. But that leaves open a possibility. I mean, that means the cross product could be either one of these vectors. I mean, both of these orange vectors that I've drawn are perpendicular to V and W. They both have length equal to the area of the parallelogram. So which one is it? Right? If I want to take a geometric description of the cross product, I kind of know which direction it's pointing, up to a possible minus sign. I know how long it is. Now I just need to worry about the minus sign. Which way does it point? So let's see here. It's orthogonal to V and W. Length is equal to the area. How do I decide on the remaining two possibilities? And the answer goes back to this formula that we were looking at, we already made sort of a convenient, tricky use of this. The fact that that's a square told us that this is positive, and therefore I don't need to deal with absolute values, and therefore, it's already a volume. I don't need to worry about absolute values. But this fact that this is a square and therefore positive also tells me that this listing is a right-hand order. Cross product V W. That's a right-hand order because the determinant's positive. Yeah? Well, that's a right-hand order. Now keep in mind, if you sort of cycle the list, that would still also be a right-hand order. So if cross VW is a right-hand order, cross VW is a right-hand order, then that means that VW cross is also a right-hand order. And this is how we decide between which of these is the right cross product. Well, VW. Look at your thumb. That make sense? Okay. So this gives us a purely geometric formulation of. Let's see here. So satisfies the right-hand rule. There we go. This is a purely geometric formulation of the cross product, and some mathematicians' books present the cross product like this. Instead of starting with a formula and deriving the geometric properties, some books start with, hey, let's define the cross product to be the unique vector satisfying these geometric properties, and then work backwards and derive the formula as a result. I think that's harder to do. It's just a little harder to work with, so I like to do it this way. Anyway, interesting facts. Okay, so we've seen a lot of information. This example is easy reading. I'm going to let y'all look at this one. Lots of interesting properties of the cross product and how that relates to determinants and right-hand order and dot products. Okay, lines and planes. We're going to do this section pretty quickly because it's pretty straightforward stuff. There's some cool tricks in here. I'm sure that y'all remember the equations of lines in the plane. Right, big yawns for y equals mx plus k. Right, what's that? 8th grade. Right. So the biggest concern I have for whether you know this formula is whether you may or may not have forgotten it. Right, but I know you've certainly seen it. Okay. Right. Then there's this other one, ax plus by equals c. And there's like, I don't know, 3 or 4 of them different sort of, everyone's got their favorite equation of a line. I used to really not like this one because where do these A and B come from? I mean, A, B. What are these numbers A, B, and C? What do they mean geometrically? It's not obvious what they if they're meaningful at all. Whereas M is a slope. That means something geometrically. I understand that, right? K. That means something geometrically. That's the y-intercept. I mean, I can see that on the picture. So I always like the first equation there because it's you can read off natural meaning from the participants in that equation. Okay. And over here, it's like, I don't know. What are A, B? What are those things? They don't seem to have anything to do with the actual line. Well, that was wrong. Turns out that A and B are very importantly connected to the equation, or to the geometric line, and I'm going to show you how that comes about. So here's a line, and I'm going to describe the line by giving you a couple of geometric features of it, and then with those geometric features being given, I'm going to derive the equation. I'm going to start with some geometry, work from that to the equation. Specifically, I'm going to tell you a point on the line, and I'm going to tell you a vector perpendicular to the line. Now, I appeal to your geometric intuition. If I say L is the unique line that goes through that point x naught and that is perpendicular to this vector n, that's a meaningful, right? That there's only one such line. Okay. All right. And now, having done that, I want to consider, how do I decide if a vector x is in the line or not in the line, right? You give me some point, algebraically, how would I go about deciding if that purple point is or is not in the line that is, through x naught perpendicular to n? Okay, and the observation I want to make is that it all boils down to this difference vector. Right, let's look at x minus x naught. If x minus x naught is parallel to the line, then x is in the line. And if x minus x naught is not parallel to the line, then x is not in the line. Right? Simple as that. It all boils down to whether that red vector is or is not parallel to L. Okay, so we'll write that down. All boils down to whether that difference vector is parallel to L. Well, wait a second. Parallel to the line would mean perpendicular to the n vector, because n is perpendicular to the line. Oh, somebody said perpendicular. That means dot product is 0. Again, I hope you all have that knee jerk, or I hope you're working on that knee jerk whenever you see the word perpendicular. It's like a Simon Says kind of a thing. If you're good at Simon Says, then you can be good at remembering this, right? I have a 4-year-old, so Simon Says has been coming up recently. Right? So that dot product. Now, why do we care about having a dot product in here? It's because this is our foot in the door to doing algebra. Right? All of this up here is geometric talk. And geometry is relatable, but it's, we can't do algebra, right? Doing algebra, I've made this case already. Algebra is a really powerful tool. So now that we have this connection to dot products, we're in the world of algebra. We distribute. We whip that term to the other side. And what we find is that we have an algebraic test. A point is on the line if and only if it satisfies this equation. This is the equation of the line. And how can I simplify that equation? Well, go back up to this picture. And notice that whatever I call the coefficients of that n vector, if I call those A and B, for example, right? They show up in the equation. Right? So this brand new, just seen it for the first time equation for the line n dot x equals n dot x naught is really just a disguised version of this old equation that we saw back in 8th grade, or again whenever that is, 9th grade, I don't know. Ax plus by equals c. Okay. So now these days, not only is this not my least favorite equation of a line, this is now my most favorite equation of the line. This is the most geometrically useful equation in the sense that these numbers, these coefficients, A and B, right? Those numbers are telling you a very important information about this vector n that is perpendicular to your line. They're telling you the geometry of a vector that's directly related to your line. And vectors are powerful objects. We've seen a lot of that recently. They're powerful objects, and it's a more sophisticated thing to have to use than a slope is, as it turns out. Okay, so there you go. So that's a flashback to high school. There's a 3-dimensional version of this, and that is if you're interested in describing a plane. So I assume you all have not seen equations of planes. If you have, cool. If you haven't, no sweat. If I want to describe a plane, I could say, look, if you give me a point in the plane and a vector perpendicular to the plane, that uniquely describes the plane, right? If you say, look, I'm looking for a vector, it's perpendicular to this vector, right? So my plane it's perpendicular to that vector. Well, there's only so many planes that are perpendicular to that vector, and exactly one of those goes through a given point. So if I give you a point and by the way, that we call it n here because this is sometimes called a normal vector. Normal in this context means perpendicular. Okay. So given a point and a normal vector, that uniquely defines the plane. And if you make the exact same argument from that, right? So we're trying to decide if this point x is in the plane or not in the plane. Well, it boils down to whether this difference vector is either parallel to the plane or not parallel to the plane. Parallel to the plane is synonymous with perpendicular to the normal vector. Orthogonal means dot product is equal to 0. Distribute. Move this term over to the other side. And there's your equation of your plane. And again, these numbers A, B, and C are very geometrically natural. Those numbers A, B, and C are simply the coordinates of the normal vector. Right? So when you see AX plus BY plus CZ equals D, just peel straight off of that equation. Oh, ABC means something. ABC is my normal vector. Sweet. Okay. All right. So here's a question we can answer with this tool. So what's the equation of the plane passing through this point and perpendicular to a certain vector? Well, this is marshmallow question in the sense that, well, this question has told us the x naught, and it has told us the normal vector. If you know the x naught and you know the normal vector, right? The normal vector goes there. The x naught goes there, and there's your equation. Okay. There's variations of this. Now here's a different question. We're going to answer with roughly the same tool, but with a little bit of preliminary work we have to do. We want to find the equation of a plane that passes through 3 given points. Now here I don't have a normal vector given. I'm thick with, we're lousy with x naughts. Pick any of these 3 points. I don't care. It doesn't matter. The x naught can be any point in the plane. We already have 3. I am a lazy person, so I tend to pick the ones that have the easiest numbers. I would encourage you, when it doesn't matter, take pity on yourself. Look at the one that has the most zeros, or the smallest integers, whatever. The one that looks the fewest square roots, if that's a worry. But pick the easiest looking number. But how do we find the normal vector? Well, if I have 3 points in the plane, then notice that means I have 2 vectors parallel to the plane. And if you have 2 vectors parallel to a plane, recall that taking their cross product will give us a vector perpendicular to both of them, and therefore a vector perpendicular to the plane. This is a really powerful trick. This is going to come up a lot. There's a lot of questions, find the equation of the plane such that blah, 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 where one of the big tricks is to find vectors parallel to the plane and then cross them. That gives you your normal vector. Right? Okay. All right, so that's what we do in this trick right here. You see there's the cross product that we make our normal vector. Okay, what if I want to describe a line in R3? Now, we've done lines in R2. That's what? Old news. 8th grade. We've done planes in R3. This is neither of those. This is a line in R3. And it's a different geometry. We're going to end up with a different sort of approach. I'm going to need to describe that line a point in the line. It's not good enough to give me a vector perpendicular to the line, because if I were to know a vector perpendicular to the line, well, there's lots of lines that are perpendicular to that. There's sort of, if you might say, a sort of a whole plane of lines that are perpendicular to that blue vector. So that's not enough information. But if I am given a vector parallel to the line, that nails it down. Right? There is exactly one line that goes through x naught and is parallel to v. Okay, well, how do I decide if a vector is in the line or not in the line? Well, I'm going to look at the difference, and I'm going to start thinking about the geometry, right? I need for that difference to be parallel to the line. Okay, so I need that difference to be parallel to v. I need that difference, therefore, to be a scalar multiple of v. Where's my, here we go. Parallel to the line means parallel to v. That means it needs to be a scalar multiple of v. Now we've got some algebra written down. Solve for x. Means x takes that form. Now, this is not what you'd call a traditional equation of the line because, the idea of an equation is that if you know the equation, somebody says, hey, I got a point here. Is this point on your object? You take that point, you plug it in, you just see, is the equation yes or no? If the equation works, then yes, it's on your geometric object. If the equation doesn't work, it's not on your geometric object. I can't really do that here. I can't just plug in an x and ask, did this equation work? Because I don't know what t is. It only needs that to be the case that this works for some value of t. And it's not clear. How would I decide whether x fits this equation for any possible value of t? That's a lot of values to check. I can't check all of them instantly, right? What do you do here? So this is not a traditional equation, but what it is it's a different thing. This is what we call a parameterization. A parameterization is not a point checker. A parameterization is a point generator. So if you come to me with a point in advance, I don't know what to do with that. But I can instead say, you know what, I'm just going to start cranking out points on this line. I can take any value of t I want, plug it in, out comes a point on the line. I can take any other value of t. We could do this all day long. You just keep giving me any real number t. I plug it in, boom, out comes a point on the line. Equations can't do that. Right? So equations can test points. Parameterizations can generate points. Okay. All right. So if you want to parameterize a line that passes through these 2 points, well, okay. Let's. How do we go about finding a parameterization? We need to find to parameterize. I need a point on the line, and I need a vector parallel to the line. I have been given in this question a point on the line and another point on the line. Given 2 points on a line, again, we're flush with choices of what to be my x naught. Take either one, A or B, I don't care. Whatever. Suit yourself. How am I going to find a vector parallel to the line? Well, how about we subtract them? That'll make v the vector parallel to the line. So there you go. V is b minus a. And then you parameterize by taking arbitrarily a as your x naught, and then plus t v, v being b minus a, and you're good. Okay. One of my favorite applications of ways that take advantage of the difference between parameterizations and equations, right? And keep in mind, an equation tests points. Parameterization doesn't. A parameterization generates points. An equation doesn't. So this next question capitalizes on the fact that these two different things serve two different roles. And here's the question. I want to find a point that's on the line in the previous example, and that is also on the plane with that certain equation. So, said differently, I've got a plane, I've got a line, and I want to find where does that line, if anywhere, where does that line intersect that plane. Now notice, the line is described by a parameterization, so I can generate points on the line. The plane is described by an equation, so I can test possible points that might come my way to see if they're on the plane. So the strategy is very simple. I'm going to generate points on the line and then test to see whether they're on the plane by plugging in the generated points into my equation, namely my point tester. That's the big idea. And so here we go. Now let me rewrite. Let's see, let me rewrite this as 4 plus 3t, 3 plus 0t, 1 plus 3t. And notice that what I have then are, x, y, and z. Right? So on my parameterized line, these are the formulas for x, y, and z. I test by plugging in those x, y, and z into my point tester. Right, we want to test, hey, there's a bunch of points on the line. I want to test and see which ones are actually on the plane. So I plug in those formulas into this equation, which becomes this. Crank. And you see that you found what t is. And of course, once you know what t is, you can plug that back into the parameterization, and that gives you your point. So, kind of a cool problem. And I'm out of time. Okay, so we will pick up here. So, I'm behind schedule as usual. I'm going to have to try to pick up the pace next time. But we did not finish this section on lines and planes. So we only finished 1.4 today. So 1.4 is what I can assign for today. Tomorrow we will definitely finish 1.5. 1.6 is quick. And then, we'll see how far we can get after that. But I'm hoping to finish a couple of more sections. So Friday we're going to finish a bunch of sections as the punchline, which means that you're going to have plenty to keep you busy over the weekend. Right? But we'll see what happens. All right, see y'all later.